Thank you. Thank you to the committee. This is work in progress, so it's not going to be very results oriented. I'm going to be mostly just talking through some of the perspectives that I have, and I would love any input on things that I'm missing and so on. So I'm at Toronto Metropolitan University in Canada. Oh, it still says Ryerson University, which is what we used to be, so that's changed. So dynamic languages are very important. They remain important. You know, they've been around for anywhere between 20 and 50 years, the ones on the list, and but they're still very important. So, and commodity computers have changed a lot over that time. Much larger memories and multiple cores. So, and the problems that we're trying to solve have gotten larger. People want to use Ruby and JavaScript to solve really big problems, and also the other languages. So what are the design principles for a modern runtime? So almost all of those runtimes, even so Smalltalk, all the Smalltalks still use a single thread of execution. Python uses a single thread of execution for the computation. They all play games to minimize the blocking of I/O, but for actual computation, they all have basically locks that really limit the parallel optimizations or operations that can take place. So modern runtime, large memories, pretty much everything is 64-bit. You can't even get something from some manufacturers that's not 64-bit anymore. And IEEE 754 is ubiquitous. And the only way to get things to run fast in modern architectures and going forward, at least until some future technology arrives, is to go with multi-cores. And the fact that most of the existing systems don't really do that is part of the problem. So I've been doing a sort of clean slate Smalltalk implementation that I call ZAG. It's, you know, clean sheet of paper, and how would we do things? The low level is implemented in a language called Zig, which is a relatively new language. And my goal is to support open Smalltalk systems, but I don't want to rewrite the user land in the process. So I want to make that as consistent as possible. However, as I was working through this and having experience in a lot of other languages as well, I was very conscious of how this could be used to support other dynamic languages. So I'm going to talk about it primarily from the Smalltalk perspective, but I have a couple slides at the end where I'm talking very much about how I think this fits into other languages. And I think as we go through, there's also a lot of things that are related to other languages as well. So I have 64-bit immediate values. That includes double floating point, 51-bit small integers, true, false, nil. All of these are a single 64-bit value, including some block closures, Unicode characters, symbols, and so on. Have a per thread copying memory arenas and stack, and a shared non-moving arena. So this is designed to be very multi-core friendly. I also have an algorithm for fast dispatch, which I'll not spend very much time talking about because I wanted to talk about this not just for object-oriented languages, but also for others. And it's very easy to generate code from an AST. Currently, I have, still this is very much work in progress, but I have a thread-coded execution and standalone export that I'm currently working on. In the future, I'll certainly want to have a JIT. Immediate value. So they're 64-bit, and I use NAND boxing, which I won't spend much time talking about. But you can look it up on lots of other places use it. This lets me give division floats, 51-bit small integers, and others all in that 64 bits. And there's room for instances of any type that has a single 32-bit value, so you could have non-memory types for other things as well, and including some kinds of block closures, which I'll talk about in a few minutes. So here are the coding, and I won't go through it in any great detail, but basically everything less than or equal to compared on an unsigned basis. Anything less than or equal to negative infinity is a double. Then we have these FFF1 tags. So any FFF is not a number in, or that's greater than infinity, is not a number in IEEE floating point, and therefore can be used. So this includes, this is the 16-bit class number, so it includes the class and 32 bits of value associated with it. So all these values are encoded. Then I also can code certain kinds of closures or thunks. So I have representations for those as well. So nil-adic, basically anything that doesn't need an actual closure can be encoded here. That basically the 48 bits that are left would be the address of the function or the closure. And that works for nil-adic, monadic, and dyadic. If you want to return self, that can also be encoded as a single value. And then, of course, we have general heap objects and small integers. So multi-core support is key to this if we want to speed up applications. I wanted to have minimal blocking. So I have computational mutator threads, and these are what all the computation happens in, and they will check periodically to see if they are supposed to interact with the global garbage collector. There are I/O threads, one per open port, and those will not retain any or retain only active links to objects. And then there's a global collector thread. So this is assumes that you'll run on, and those threads, obviously, if you're running on a single processor, those could be, they would be time shared. But if you had a multi-threaded architecture, then you would be able to run completely in parallel. Mutator threads use a copying collector with a private nursery and 2 Tina arenas. And it actually copies things back and forth between the Tina arenas for 4 or 5 times before they get promoted. So if a value is in the nursery, it gets copied. So it's sort of you could kind of think of it as a 5-generational architecture using copying collectors per thread. And the reason for that is that per thread, there is no possibility. So a thread's data is not accessible by anybody else, and therefore we don't have to worry about any contention, so copying collectors work fine. As I said, they check periodically to see if they are supposed to interact with the global stack, the global arena, and mark them. I/O threads just maintain a list of shared buffers, and the global collector thread manages a non-moving mark sweep arena. It periodically goes and does a mark by asking, well, first of all, it marks all the static things that it knows about, and then it asks the mutators for their global roots, and then the mutators will each do a garbage collection and identify all the shared roots, global roots, and mark those. Keeps doing this until all the roots have been found, and then we can proceed to sweep. But this is non-moving. So the challenge is how do we handle, we don't want memory to just grow and grow and grow. So it uses a global collector for non-moving mark and sweep. It uses a linked free list heap, similar to MIST, if that means anything to people. And anything that is very large will use a separately mapped page. So the instance variables and the object would be in the general global heap, but the actual data would be in separately mapped pages. And this means if you map a multi-megabyte file or something, it's not going to have to stick around after it's no longer used, which would happen if it was just mapped in as an ordinary object. I have a unified dispatch model, which uses a single level of hashing for method dispatch. It falls back to multi-level where necessary, but so each dispatch table has an entry for each method that's been sent. Uses near perfect hash using phi hashing. And the reason for this, for the single level of hashing for method dispatch, is in a multi-processing environment, we need to be able to have dispatch work quickly. But the optimizations, the Deutsch optimizations for dispatch don't work well in multi-core environments because you actually modify methods in place, and that is not going to work well without putting in all sorts of unnecessary and complicated locks. So this way we don't have any such locks, and we get reasonably good optimization. Another reason for this single level of hashing is that it means that we will inline, which I may have in the next slide. Yeah, high performance inlining. So we can inline fairly aggressively because, and one of the challenges of particularly Smalltalk is that many methods are, a couple lines of code or less, and so you don't have much opportunity for inlining. By having these single dispatches, a single level dispatch, it supports inlining all of the appropriate things. So things that are references to self or super can be inlined. Methods, if we know the type of something, we can inline that. And self, we know exactly the type because the code is being generated at the leaf class level. Then we actually know we don't have to worry about something being overridden by a lower class because that would have been compiled in that class, not in this class. So methods with small numbers of implementations can be inlined, and we do this rather than the heuristic that most Smalltalk systems use of inlining if true and if while true and things like that. The inlining prevents creation of many blocks and provides large compilation units for optimizations. Code generation, we have three models. One is threaded execution. So a method is a sequence of function addresses, and Zig has a very nice way of doing tail call elimination. So these are treated as a sequence of tail calls as part of the threaded execution, and we pass along these 5 values: the program counter, stack pointer, heap pointer, thread, and the context, current context. And because we're only passing a small number of these, they actually will remain in registers, and each threaded block will pass along control to the next one, and generally passes most of these parameters unchanged or changing 1 or 2 of them. So those registers are used very efficiently. This is used for primitives and control implementations. JIT, I'll skip over. Whoops, didn't mean to do what I just did. JIT, I'll skip over, except for mentioning that it uses continuation passing style. So basically, it still uses tail call elimination to pass control so that it can smoothly and without any interference pass control between JITted or standalone code and threaded execution code. So there's no complex trampolines that have to be executed to switch between code. If the threaded code starts with the address of a JIT code or a standalone generated code, then it just goes into that code and everything executes normally. And then on return, if you're returning from native code and you need to go into the threaded execution, it will call, or the return address will be a one-line method that simply restarts into the primitive or into the threaded execution. So this transition between these is typically a couple of instructions each way. So the standalone generator is an upfront version, and it generates fairly good code. Contexts are created lazily, so we don't use native stack frames because that makes life much more complicated for garbage collection. So we allocate in the nursery heap, the stack grows down and the heap grows up, as is fairly common. And the context will be allocated in that stack. They're created lazily. So if a method doesn't send a message, then we don't have to create a context for it. We can just reference using the stack. They're created on the stack in stack order. So that means that returning from them just means bumping the stack pointer. So we get all the efficiencies of that. And the objects we don't even fully complete them unless the context needs to be moved to the heap. So as long as the context stays on the stack, so what we do update when the object or the context is created is we write a 0 to the header because that works. And then we set the previous context, the method, and clear all the locals to nil. But otherwise, we don't have to do anything. If it gets promoted, then we have to update the size and the header and the native PC. So it keeps track of the threaded PC and a native PC. I won't go into the details because I'm probably going to run out of time anyway. Supported control abstraction. So this is things that it supports or will support. I have the mechanisms worked out to support all of these, all in constant time. So it has, and this is for supporting other languages particularly. So we have full closures. We have non-local returns to support Smalltalk and some of the other control abstractions. We can do call with current continuation from Scheme. We can do yield from Ruby. We can do generators from lots of things, and coroutines. And all of these are constant time because the contexts are full feature contexts. They just don't cost very much to create because we do it lazily on the stack. I have very limited results. I have a simple Fibonacci function, and this is perhaps slightly interesting, but basically the first line is Pharaoh. I'll just go through the arch ones. So that's running on Pharaoh. Fib native is the code written in Zig, basically transliterated to Zig. And so that's the target. That's as good as we could possibly do. An object version just shows the overhead of using dynamic typing rather than static typing. So Fib object uses 64-bit integers. Fib object uses actual objects, so that is the best that we could do, retaining the dynamic execution. Fib comp is the hand-compiled native code that would be generated ideally at least by a JIT or by the native exporter. Fib thread is the threaded execution. So I'm quite pleased that that's only about 4 times slower than the comp version, and it is somewhat smaller, but not wildly smaller. Just for comparison, I wrote a bytecode interpreter executing the same code as the thread interpreter, and as you see, it's about 7 times slower. So my hope is that I'm going to get pretty reasonable expectation when I can run, or performance when I can run a run real benchmarks. Okay, and then the only interesting thing about the others is that the Fib native on an x64 system, x86-64, is somewhat faster, but the difference is by the time we get to the comp version and the thread version, the times are quite comparable. But the native and object are quite different. So on the x86, going to dynamic typing slowed down quite significantly. whereas on the ARH64, it had very little effect. And that's it for conclusions. Moving towards a high-performance Smalltalk, and want to support other languages as well. Hopefully, I will have students that will do some of the implementation for other languages, and be very interested in people's comments, or go and look at the code and contribute or comment there. Thank you.
Well, we get the microphone around. Maybe just, I haven't really heard of Zig before. Can you just give us a little bit of a taste of what's special about Zig as a programming language?
Zig is a C replacement. So I originally started doing this work in Rust, and but I came to realize that Rust is a C++ replacement, not a C replacement, and some of the low-level things that I was trying to do are quite challenging. Zig is a really interesting language. It has first-class types. It has compile-time execution of Zig code, and it uses this to create generic types. So the implementation of the byte code interpreter was a fairly, well, took a bit of time to parameterize it, but uses many of the same pieces as the threaded interpreter by using the generics. So I strongly encourage you. It's basically I will program in 3 languages: Smalltalk, Zig, or Rust. And Zig is a pretty interesting language.
All right.
Let me also say it's completely compatible with C. So in fact, you can compile C code with the Zig compiler. So the compatibility is extremely high there.
Who has any comments, questions for Dave? Jeremy? Thank you, Jeremy.
Hello. I'm interested in lazy evaluation. Does your framework at the moment readily support languages with lazy evaluation strategies like Haskell?
I haven't thought of that because when I think lazy evaluation, I think Haskell and I think static typing. So I haven't thought very hard about that. But I mean, certainly there are, it could be supported. Whether it would be very efficient or not is another question. I haven't really thought of good angles on how to do that. But that's a really good question. I'll certainly put it on my to think about list.
Okay. I have another question. So you are kind of using Smalltalk as a mold, also kind of looking at different languages. But Smalltalk, for when it comes to dynamic languages, I would say is actually rather static in many ways. And one of them is the data representations that it provides. So you have your pretty much fixed classes with fixed object layouts. But if you look at languages like Python, JavaScript, or Ruby, for instance, then we suddenly have objects with very flexible and perhaps even prototype-based approaches. So do you have any thoughts on how to support kind of these flexible object models?
I would be interested to maybe have an offline conversation about that, because I don't quite see it that way. I see Ruby and Smalltalk as being almost interchangeable, and Python as well seems to be, to me, pretty much a subset. But maybe I'm missing something important.
So in Ruby, you can also add dynamically fields at runtime to an object, which is something you can't really do with Object. I mean, in Smalltalk, you can become and things, right? You can dynamically create a new class and then have an object that becomes another object. And,
you can dynamically add fields to a class too.
Right, but in Smalltalk,
Yes.
that's usually realized by kind of updating the objects and kind of creating possibly even a new object with a new layout. While in, well, maybe that's not to use Ruby, but Python or JavaScript, you really look at the objects like hash tables.
Yes.
So, and indeed, people write a lot of code that is actually quite dynamic, and especially when you take JavaScript, JavaScript implementations typically kind of have some kind of object shape representation, and there will be a talk later this afternoon on one of the techniques people may want to use there. But it's kind of, yeah, it's very dynamic. It's because you don't really have the notion of a class. Runtimes try
Yes.
to infer this after the fact.
Yeah, I've certainly thought about about how to support JavaScript and those sort of dynamic dispatch of dynamic fields. So I've got some ideas on that. It's not my biggest, not the thing I've spent the most time thinking about, but I've thought a bit about that. Thank you.
Do we have any other questions? Okay, then let's thank Dave again.